Okay.
So,
Did you say integrating?
yeah, so it's like, I don't know, 2 cosine x plus 1 equals 0, solving stuff like that.
Okay. You want to verbalize some problems and we'll go through them?
Yeah. Let's say. Okay, one I had trouble with was 3 secant squared of x minus 4 equals 0.
Okay. Solve these just like you would an algebra problem.
Mm-hmm.
What's the first thing you're going to do?
Move 4 to the other side.
And the second thing?
And divide by 3.
And the third thing?
Square root it.
So what's secant x equal?
2 over root 3.
Plus or minus.
Oh, right.
And that's an important one because that's going to give you 2 extra solutions.
Mm-hmm.
And it is 2 over root 3. And let's leave it like that for the moment. Because if we look at our 30-60 triangle, it's 1 root 3, 2.
Mm-hmm.
So 2 over root 3 is secant of what angle?
30.
Okay, so we're looking at a raw angle of 30.
Mm-hmm.
And it was actually better not to rationalize that. It allowed us to figure it out a little easier by not rationalizing it. Now, that's not the only solution. Since it's plus or minus, were you given constraints that x is between 0 and 2 pi?
No.
So they want you to come up with the, okay, what are all 4 angles in the unit circle going to be?
They're going to be 30, 150, and 210, and 330.
Okay. Now, because they didn't put a domain on there, if they'd have said between 0 and 2 pi, we'd be done.
Yeah.
But in reality, all coterminal angles work. So it's really that plus n or 2 pi k or 2 pi n. Do you guys use a particular letter?
We do 2n pi, or 2 pi n.
2 pi n. Okay. And you can add that to each of these.
Okay.
Where n counts from 0 up.
But because some of those are like 180 degrees away from each other, don't you take out 2 of them and just do...
Ah, yes. Yeah. In fact, it's the first one plus pi n, isn't it? In other words, if I do that, that takes care of that one also. And if I do that, that takes care of that one. So that gives me 30, it gives me 210, gives me 150, and it gives me 330.
Mm-hmm.
So yeah, this is, I didn't think about doing that. But yeah, that should be your answer. Well,
Okay.
assuming they want it in degrees. They may want it in radians, especially since I put pi there. So it probably makes a little more sense to have pi over 6 and 5 pi over 6. Plus pi n, yeah. Okay.
Then we have 4 cosine squared x minus 1 equals 0. And he wants these in terms of radians.
Okay. Where's cosine of x equal to 1/2?
At pi over 6.
Pi over 3.
Oh.
Always remember sine of 30 degrees is 1/2 and cosine of 60 degrees is 1/2.
Mm.
And I believe this is going to be exactly like the other one. It's going to be plus pi n. And we need the second quadrant, which would be what?
2 pi over 3.
Yeah, that's the negative one. Okay?
Okay.
Incidentally, there's another way to look at this problem. We solved it very algebraically, but one way you'll never forget to put the plus or minus is if you solve it as the difference of perfect squares.
Mm-hmm.
Then you'll get cosine x equals plus 1/2, cosine x equals minus 1/2.
Okay. We can do, so these are in the interval of 0 to 2 pi.
Okay.
So 3 tangent cubed x equals tangent of x.
Okay. What's the thing you don't want to do here? That's tempting to do.
Divide.
Yes. Divide both sides by tan x.
Yeah.
Isn't that tempting to do?
Yeah.
The reason you can't do it is because if tan x is equal to 0, you lose that solution completely.
Mm-hmm.
Notice you'd end up with tan squared of x equals 1/3, tan x equals the square root of 1/3, but you don't have the 0 solution, and yet 0 clearly is a solution here for x. And the way you get it is by subtracting tan x from both sides, factoring it out, solving it now algebraically. In other words, tan x could be equal to 0, or tan squared of x equals 1/3, which makes tan x equal to 1 over root 3.
Mm-hmm.
What angle is tan x equal to 1 over root 3?
Pi over 6. Or pi over, yeah, pi over 6.
You're right, pi over 6. It's the 30 degree. The easy way to convert radians and angles is this times this is always 180. As long as this is a 1. 1 pi. If it's not 2 pi, it's always 1/8. In other words, pi over 4 is 45 degrees, pi over 3 is 60, and pi over 6 is 30. That's the way I like to remember it. So, since I'm in the unit circle, what are my answers going to be?
Gonna be pi over 6, and then
that's the first quadrant for this one.
7 pi over 6.
Yeah. And this one is 0, and where else?
I'm not sure.
The period on tangent is pi. So every
Oh,
pi, it repeats itself.
So 0, then pi.
So there's your 4 solutions.
Okay.
Now, we did start late, so I don't mind going to like 7:15. That's fine. I want to make sure, though, that we get to this kind of a problem. You know how to do that problem? With theta being between, well, first of all, let me ask you if you've gotten any of these. Where this is not trivial to solve.
Oh, is this the one where theta is gonna become between like
0 and 8 pi. Exactly.
Yeah.
That's exactly the way you do it. In other words, let's go through this. Since theta's domain is 0 to 2 pi, well then 4 theta's domain is 0 to 8 pi. So if I'm solving for 4 theta, I have to take it all the way out to 8 pi. Well, we know that 4 pi can be pi over 6. That's 1, right? And positive half is 5 pi over 6. And then just add 2 pi to each of these. So 13 pi over 6. This is the second unit circle. I'm adding 12 pi over 6, 12 pi over 6 to each one. That takes me out to 4 pi. And I have to add 12 to this one, 25 pi over 6, 12 to this one, 29 pi over 6, 12, what was that, 25? Yeah. 12 to that one, 37 pi over 6, and finally 41 pi over 6. So those are all of the solutions for 4 theta. 1, 2, 3, 4, 5, 6, 7, 8. So what's theta going to be?
Theta is going to be all of those divided by 4.
Yeah. And notice, so this is pi over 24. That's a solution. If I get down to this one, that's 41 pi over 24. Notice that all 8 solutions are now between 0 and 2 pi for theta.
Yeah.
But the mistake most people will make on this is they won't expand their domain. They'll only come up with those 2 answers, which means they'll only come up with pi over 24 and 5 pi over 24. They'll come up with 2 answers instead of 8. All right, I wanted to make sure we got to that. That's one of the few trig problems I know that can be pretty tricky if you're not used to handling it.
Yeah.
Go ahead with others if you want.
2 secant squared x plus tan squared x minus 3 equals 0.
Okay. What should we do here?
Move 3 to the other side.
Okay. Now what?
Then no. Probably make it so.
There's a trig identity that relates secant squared and tangent squared. You know what it?
Yeah.
You remember what it is?
Tan squared plus 1 equals secant squared.
Which one should we plug in?
I'd say tan squared.
Only problem is then we're going to have to solve a secant problem.
Oh, that's true.
So I'd plug into the secant squared. At least then we have a tangent problem. I don't know about you, but I'm far more comfortable working in the first 3 trig functions, sine, cosine, and tangent, than I am secant, cosecant, and cotangent. I always kind of have to treat it. It's hard for me to think. It's kind of like degrees and radians. I now can think in radians, but I still don't think in secant, cosecant, and cotangent. I tend to think in sine. And also your calculator only has the first 3. So it's easier, especially if you're using a calculator, it's much easier to solve the problem if we have it in tan than secant. So I'm going to multiply, or I'm going to substitute tan squared plus 1 for secant. And now the problem is going to almost solve itself. We're going to, what next?
Distribute.
Distribute and combine like terms. So we got 2 tan squared plus another one. We're going to have 3 tan squared. We got 2 we're going to take on the other side.
Divided by 3.
Tan equals 1 over root 3. Plus or minus. Can't believe I did it. Much as I rag on my students for always leaving that out.
Yeah.
Okay, so we're talking a 30-degree angle, pi over 6. The equivalent of that in all 4 quadrants. Assuming this was from 0 to 2 pi, right?
Yeah.
Okay. So pi over 6, what's the second one?
5 pi over 6.
Third one?
7 pi over 6.
And the fourth one?
11 pi over 6.
Okay.
Alright. 2, no.
There must be some there where you have to treat it as a quadratic in order to solve it. In other words, yeah, where you have a squared term, you have a non-squared term, and you have a constant.
Yeah.
Okay.
2 cosine squared x plus cosine squared, or cosine x minus 1.
Oops, I don't want to do that. Right after I tell you how I'm going to solve it, I do that. Okay, so this just becomes a factoring problem. If you like, think of it as u equals cosine x, and we would now have 2u squared plus u minus 1. Factor that, but if you don't have to do that substitution, it's worth not doing it. So what goes here?
2 cosine.
What goes here?
Cosine.
We know the signs are opposite, but it might be this way or it might be this way. So let's see, we have a plus term in the middle. We must have to multiply that 2 by the 1 there, like that. And that produces that. So now, what next?
You just keep those as separate terms and solve that way, right?
Yeah, set each one of them equal to 0.
Yeah.
So one solution is cosine x equals 1/2. The other solution is cosine x equals -1. So x is what? This, again, 0 to 2 pi?
Yes.
Okay.
So cosine, that's going to be pi over 3. Wait.
It's 60 degrees.
And then that one's going to be...
What's the other one inside the fourth quadrant?
Oh, right. It's 5 pi over 6. Or 5 pi
5 pi over 3. Yeah, take 2 pi and subtract that.
Yeah.
Which is 6 pi over 3 minus pi over 3 is 5 pi over 3. So that's those two solutions. Where's cosine x equal -1?
Pi.
And there's only one solution there. Okay?
All right.
And the only other problem I can think of that can be a little tricky would be this one. Oh, sorry. You have any that look like this?
Kind of. I have a cosecant.
Well, let's look at this one because remember the cosine, the double angle formula for cosine? There's 3 different identities for it. One of the reasons is a problem like this. In other words, cosine of 2x equals cosine squared minus sine squared. It's also equal to 1 minus 2 sine squared. And it's also equal to 2 cosine squared minus 1. So which one am I going to use?
The 1 minus 2 sine squared.
Yeah, because that's going to give us a quadratic. So then we're going to have a perfect quadratic. And I just made this up off the top of my head, so let's make that 2 or something. But then you'd use this. Now, it is possible to get a quadratic that you can't factor, and you actually have to use the quadratic formula on. I don't know if you would ever get anything like that. Let's just talk briefly about it because it isn't exactly clear what you would do. In other words, let's have this. Doesn't factor, got to use the quadratic. So what am I going to write?
X equals negative...
Not x.
Sine of x equals...
That's the tricky part. It's real tempting to say x, and then you get lost because you don't know what you're looking at when you see an answer. But if sine x equals whatever we get from the quadratic, now I have to take the inverse to find out the answer. In other words, what do we have? -1 plus or minus the square root of 1 minus 12 or plus 12 all over 2. So we get -1 plus or minus root 13. So that's what sine x is equal to. So if I want to know what x is equal to, it's the inverse sine of those two numbers. And whatever angles those gives you, that's the answer.
Okay.
Okay. I'm giving you all the tough ones that I can think of. It may be tougher than what you'll see, but better that than the other way around.
Yeah. Do we have time for one more?
Sure.
Cosecant x plus cotangent x equals 1.
Let's see. Could square both sides. Yeah, let's do that. Not sure this is the fastest way to solve it, but I can at least see the light from this solution. I've squared both sides. What's cosecant squared x plus cotangent squared x equal to?
Plus cotangent?
Yeah, we've got cotangent squared plus 1 equals cosecant squared. So, oh boy. I thought I was going to be able to use the substitution. I can't. Well, I can still substitute for that. Let's substitute cotangent squared plus 1. Now I have the 1 goes away, and I have 2 cotangent squared plus 2 cosecant cotangent equals 0. Divide both sides by 2. Factor out a cotangent. We're not much closer to our... Oh, yes, we are. Notice what we have here. Gosh, how did I get this? I don't think I've ever solved anything that came out like this. I feel like I almost made a mistake. Cotangent x plus cosecant x is 1, right?
Oh, isn't it cotangent x plus 1? Wait, is it?
Yeah, in other words, the beginning of the problem, that was the equation. How to solve that equation.
Oh, right.
Well, I can use that, substitute 1, which means this has to be 0, which means x has to be equal to pi over 2, which is where cotangent x is equal to 0. And third quadrant would, oh, hold on. No, I just add pi, so 3 pi over 2. There's your two answers right there. I don't like the way I did this one. I can never recall doing an algebraic solution and then having to substitute what I started with.
Yeah.
Makes me think that there's a far easier way to do this. Well, I can see one. Yeah, let's switch them to sine and cosine. This is 1 over sine. plus cosine over sine, right?
Mm-hmm.
So now we have 1 plus cosine over sine equaling 1, which means x can't be 0. Well, yeah, x can't be 0 anyway because that's undefined at x equals 0. So I know sine x can't be 0, so I can multiply it by both sides. Does that help? Doesn't, does it?
Unless you squared both sides and then converted sine x to a cosine.
Yeah, we could do that. That's the same process as we did the first time through, really.
Oh, yeah.
I mean, it's not really any different. I'm just using the reciprocal functions. What am I missing? I'm pretty sure the way I solved it the first time through was legit. But it was strange.
Yeah.
Let me pull up Wolfram Alpha and stick this in there and see what they come up with a solution. What was my solutions? Pi and 3 pi over 2?
Yeah.
Is it cosecant x plus cotangent x equals 1?
Mm-hmm.
So when n is 0, we have pi over 2. When n is 1, we have 3 pi over 2. Oh, no, we don't. Let's see. When n is 1, we have 1/2 times 5 pi?
Hmm.
That's weird. Z is the set of integers starting at 0. Does 0? Yeah, 0 gives you pi over 2. But then when I put in, how can the next solution not be 3 pi over 2? That's the only, in other words, if I look at the cotan curve goes like this. That's pi over 2. And it repeats every pi. It's got a period of pi. So that's got to be 3 pi over 2. Am I reading this solution in Wolfram Alpha wrong? I might be. Looks to me like they have the parentheses wrong. That parentheses should go right there, and then it would work just fine.
Right.
When n is 0, it would be pi over 2. When n is 1, it would be 3 pi over 2. Or wouldn't it? No, when n is 1, it would be... Yeah, I'm going to have to look at that a little bit. Maybe I can enlighten the situation next time on that solution. All right. Any last problems that you want to look at or talk about?
No, I'm pretty good.
Okay. Griffin, have a good one. I'll talk to you next time.
You too.
All right. Bye-bye.